Welcome! Today, we're diving into the chemical personalities of the elements. We're going to find out why some are these aggressive reaction seekers, why some are just perfectly content and stable, and why this whole group in the middle are kind of like the versatile, colorful artists of the periodic table.
So it really all boils down to this one question. What's the deal? And the answer? Well, it's not in the nucleus. It's all about the cloud of electrons that surrounds it, and specifically how those outermost electrons are arranged. I promise, by the end of this, you'll see how just one single electron in the right or wrong spot changes absolutely everything.
So, here's our game plan. We'll start at the superreactive edge with the halogens, then we'll meet their super-chilled neighbors, the noble gases. After that, we're jumping into the huge, colorful world of the D-block metals to figure out their secrets. Before we wrap it all up,
Okay, let's get right into it. We're going to start over on the right-hand edge of the periodic table. This is a place of real chemical extremes, and it perfectly sets the stage for our entire story.
First up, Group 17, the halogens. I like to call these the periodic table's aggressors. They are just incredibly reactive, always looking to pick a fight and start a chemical reaction. And you know what? There's a really simple reason for that confrontational nature.
just look at their outer shells. Fluorine, chlorine, bromine. You see the pattern? They all share this Ns² NP5 configuration. If you count them up, that's 7 valence electrons. They are just 1 electron away from that perfectly stable, complete shell of 8. And that one single empty spot, well, that's the source of all their drama. And this desperate need for one more electron, it has huge consequences. It gives them a really high effective nuclear charge. That just means the positive charge from their nucleus isn't shielded very well, so it can pull really strongly on any outside electrons. This makes them pretty small for their period and gives them the highest electronegativity values on the table. They are just incredibly electron greedy.
And here we can see that reactivity in action. This is a typical lab prep for chlorine gas. You react manganese dioxide with hydrochloric acid. In this case, the manganese is better at attracting electrons, so it just rips an electron off the chloride ions. This frees up the chlorine atoms, which then pair up to form that pure chlorine gas, Cl2.
Now, when halogens bond with hydrogen, we see this really fascinating trend. The bond between hydrogen and fluorine, it's super short and really strong. But as you go down the group to iodine, the atoms get way bigger, the bond gets longer, and it gets a lot weaker. And a weaker bond means it's much easier to break and let go of that hydrogen as a proton, which is literally the definition of an acid. So while hydrogen fluoride is a pretty weak acid, hydrogen iodide is one of the strongest acids we know of.
Okay, now let's just take one single step to the right on the periodic table. Right next door to those aggressive halogens, we find their total opposite. Group 18, the noble gases. These are the chemical aristocrats. They're famously unreactive and just supremely stable. So what's their secret? It all comes back to their electron configuration. Unlike the halogens, the noble gases have a perfectly full outer shell, Ns² NP6. They have all 8 electrons. They've achieved a kind of chemical nirvana. There is zero drive to gain or lose electrons, which gives them insanely high ionization energies. You need a massive amount of energy to rip an electron away from them. They just do not want to react.
You know, this stability is so profound that for the longest time, chemists were convinced they formed no compounds at all. It was basically law. And as you can see from this quote, for the lightest ones in the group, helium and neon, that's actually still true. They are the most inert elements known to exist.
But there's always a but in chemistry, right? Chemistry is full of surprises. Back in 1962, a chemist named Neil Bartlett did the impossible. He found that xenon, one of the heavier noble gases, could actually be forced to react. This was a total game changer, and it led to the discovery of whole families of new molecules with these incredible, precise shapes, like this perfect square planar xenon tetrafluoride. It just goes to show even the noble can be convinced to form bonds.
Okay, we've explored the extremes. Now let's move from the edges to the vast, bustling center of the table, the D block, or what we call the transition metals. If the halogens are aggressors and noble gases are elitists, then these guys are the versatile artists, capable of a huge range of chemical behaviors.
Their whole secret lies in their d orbitals. Now, as we move across the row and fill them up with electrons, something kind of weird happens when we get to chromium and copper.
They break the rules. Instead of sticking to the normal pattern, they actually promote an electron to get a more stable, half-filled or completely filled d subshell. This is our first big clue that there's some really unique quantum stuff going on in this block.
And here's another puzzle for you. Normally, as you go down a group, atoms are supposed to get bigger, right? More electron shells, more size, and they do, going from the 3D to the 4D series. But then look at the 5D series. Whoa! They're almost exactly the same size as the 4D elements right above them. So why aren't they bigger? What's going on here?
Well, the answer is this fascinating phenomenon called the Lanthanide contraction. See, to get to the 5D metals, you first have to fill up the 14 elements in the 4f orbitals. That's the lanthanides. And it turns out electrons in these f orbitals are terrible at shielding. Think of it like a lousy umbrella. They don't block the outer electrons from feeling the huge positive charge of the nucleus. The result? That powerful nuclear pull reaches out and just squeezes the whole atom, making the 5D metals surprisingly small and incredibly dense.
It's this complex electron structure that makes them such incredible artists. Unlike most main group elements that kind of lock into one or two oxidation states, these transition metals can have a whole bunch of them. The d electrons are super close in energy to the outer s electrons, which allows for all this flexibility. Take manganese, for instance. It can have every single oxidation state from +2 all the way up to a whopping +7. This adaptability is exactly why they're so essential as catalysts, both in our bodies and in industry. All right, and now for maybe the most visually stunning property of the transition metals. Their vibrant, varied colors. And you should know, this is no accident. It's a direct result of those partially filled d orbitals we keep talking about. The main reason for all this color is something called a dd transition. When a transition metal ion is surrounded by other molecules, its d orbitals actually split into different energy levels. So when white light hits the complex, an electron can absorb a photon of a very specific color, let's say orange, and use that energy to jump up to a higher d orbital. The light that isn't absorbed, in this case blue, is what passes through to our eyes. So what we see is the leftover color. The complex appears blue. So, the absolute key here is you need a partially filled d subshell for this to work. An iron I2 complex is pale green because it has d electrons that can make that jump. But look at a zinc I2 compound. It's just white, colorless. Why? Because its d orbitals are completely full. There are no open spots for an electron to jump into. No dd transition means no color. It's as simple as that.
But wait a minute. Some colors are just way too intense to be explained by these little dd jumps. The brilliant deep purple of the permanganate ion, that comes from a totally different, much more powerful mechanism called charge transfer. In this case, light gives an electron enough energy to make a huge leap, not just between d orbitals, but from an oxygen atom all the way over to the manganese center. This process absorbs light way more strongly, creating these incredibly vibrant colors.
Okay, let's bring it all home. We've taken quite a journey, from the reactive edge of the periodic table, through the stable land of nobility, and right into the complex, colorful heart of the D block.
So when you boil it all down, it really does all come back to the electrons. The halogens are aggressive because they're just one electron short of a happy octet. The noble gases are aloof and stable because their electron shells are perfectly, completely full. And the transition metals? They're the versatile artists. All because their partially filled d orbitals open up a whole world of complex bonding, multiple oxidation states, and of course, beautiful colors.
And that leaves us with one last thought. These fundamental rules about electron configurations, they're not just abstract ideas in a textbook. They govern how enzymes work in our bodies, how efficient the industrial catalysts that build our world are, and even create the brilliant colors of sapphires and rubies. It's a pretty powerful reminder that our entire world is built on these simple yet incredibly elegant electronic principles.